So today we have another application of the definite integral, and we're talking about arc length. And so first we just want to define something. It's called a rectifiable curve. That's a great word. And basically it's a curve that has a finite arc length. Now for a curve to be rectifiable, it has to be continuously differentiable and smooth over a certain interval. Okay, so it's not all jagged and it doesn't have holes or asymptotes or anything. It's going to be continuous there. So here's what we're trying to do. Here we have a rectifiable curve, and we want to find our arc length from one point to another point. So calculus is pretty awesome because it's going to allow us to find that length. Yep, we can tell exactly how long that is. Okay, so what we're going to do is we're going to transform our distance formula into the arc length formula using our calculus techniques. So we're just going to label this point right here. This is going to be A. And this is going to be B. So we want to find the arc length of this curve from A to B. And what we're going to do is kind of take our calculus techniques, and we already know one distance formula, right? And this is just the distance between any 2 points
Of a straight line.
of a straight line. Okay, so you guys remember that formula from your Algebra 1 days? So basically, what we can do is we can divide this up into different segments. Okay, now if we took all 3 of those segments, that would be an approximation for the length of this arc. Everybody agree? Now what happens is, the more and more points we put on this curve, and the more and more segments we create, a closer approximation we're going to get. Okay, so let's just kind of set this up to see how this is going to work. So we're going to call this x sub 0. We'll call our next x coordinate x sub 1. Our next one x sub 2. And then B we're going to call x sub n. And so let's label all these points.
Like infinity?
Yeah, n could be anywhere.
Okay.
So we can pick as many points as we want along here. The more points we pick, the closer our approximation is going to be. Alright, so this point would be x sub 0, comma, y sub 0. This point would be x sub 1, comma, y sub 1. This point, x sub 2, comma, y sub 2. And then our last point will be x sub n, comma, y sub n. So now instead of using D to represent the length between the line, we're going to say S is going to represent our arc length. And we're going to use summation notation here that we learned earlier this semester. Okay, so we want all the i's from 1 to n. And we're going to transform this distance formula now to represent what's going on right here. So if I do x sub 2 minus x sub 1, that is really the difference between the x's, right? That's all it is. And so we're going to rewrite this as delta x sub I. It's the change in x. Okay, and we're going to use I and then I minus 1 but we'll just say the change in x. And then what would y2 minus y1? How could we write this? Delta y1. Delta yi. Okay. Are we okay making that jump there from the very static to the dynamic here? This is taking the sum of all of these segments put together.
So it'd be like x sub 0 minus x sub 1 minus x sub 2 minus x sub n equals.
Exactly. Exactly. So now we're going to manipulate this a little bit so that we can eventually turn this into an integral. And this is where, you know, some smart people figured some of this stuff out.
Wait, so do we actually have to know these steps, or is this just proving how you get that formula?
This is proving how we get that formula. All right. And so the first thing we want to do is we're going to multiply times delta x sub I squared over delta x sub I squared. Okay, and this is one of our keys to doing this. So notice we didn't change anything because we're still multiplying by 1. Okay. And so the way we can combine this now is to have delta y sub I over delta x sub I squared and then times delta x sub I squared. Is everyone okay with that? Seeing what we did there? Now you're going to see why we did that in just a second. So in this radical now, we're going to factor out the greatest common factor of delta x sub I squared.
Delta x squared.
Okay. So if we factor out delta x sub I squared, we're left with I hate you never know how far to make your square root symbols.
What exactly did you just factor out what?
I factored out delta x sub I from both of these terms. Delta x sub I squared. See that? So it just draws out of this one and it draws out of this one, and that's what we're left with.
Why is the second one?
I see the pretty picture of
When
the
you
variant.
multiply it, why is that the second one?
So let's think about if we distributed this,
Uh-huh.
this times this, does it give me that?
Oh, I see.
And then this times this, does it give me this?
Oh, you just put that. Okay.
I just put it on,
You just put it there.
I put the factor in the back.
Wait, why?
Okay,
It
so
wouldn't
that
give you.
confused me a
It
little
wouldn't give you change in x sub I. It'd give you 4 to the 4, or it'd give you what? How?
So I just factored, see the common term right
yeah,
here?
yeah. But change in x sub I squared times 1 squared. Wouldn't that give you?
Oh, 1 squared is just 1.
Yeah.
Okay. Now, because this is all multiplication under our radical, we can actually take the square root of this. Okay, and we have 1.
Sorry. Wood. Sure it wasn't.
Okay. See what we did there? So here,
Slope and dx. Is that a slope squared?
yes. So very, very good, Cody. So you're seeing delta y over delta x. That is just your slope, right?
Yep.
Now in calculus, what else do we call the slope? The derivative. Okay, so this is the key that we need to see here. That this really is the derivative. We're going to call that f prime of x. And then delta x is really dx. Okay, now how do we find a good approximation of the curve if this is our summation? The step before the integral.
Set the delta as to
Yeah, set the delta to 0. So we want the limit as our deltas go to 0 of the summation I equals 1 to n. 1 plus, now we're going to change this to f prime. We're not going to use x right now. Remember, if we just chose any arbitrary x, we called it c. Some c on the interval. Okay, and now when we take the limit, we know it's the same as taking the integral from a to b of the square root of 1 plus the derivative of our function squared, and then dx. So we basically just proved how we came up with this.
Oh.
So it's not some formula that just came out of thin air. It's the distance formula taken many, many times and letting the points get closer and closer together until they're basically touching each other. So let's work on applying this now. So here's our function, y equals x cubed over 6 plus 1 over 2x. And we want to find the arc length from 1/2 over to 2.
So you'll use 1/2 and 2 as your, sorry.
Okay. The first thing we want to do for all these problems is we need to find our y prime, or the derivative of our function. So now we got to think about first semester way back when. So remember the power rule? The 3 is going to go in front of the x.
Oh, yay.
And then we decrease the power by 1. Now remember when x is in the denominator, that really means x to the -1. So we want to actually change this to negative. And then if we lower -1 by 1, now we're at -2. So it becomes squared down here. Okay. And if we reduce this, we get x squared over 2. And that's our y
Minus
prime there. 1 over 2x squared. Now we just set up our definite integral. So s equals definite integral from 1/2 to 2, because that's what we're trying to find. We have the square root of 1 plus y prime squared. And then dx. Okay. Now, when you're doing this, it sometimes can be pretty confusing, especially if you have this calculator instead of the 84. Because the 84 makes it nice and easy and it shows you the exponents where everything is. So the parentheses are the problem here. Okay? So let's just write it out how our calculator would see it. So the square root opens up a parentheses. And we have 1 plus, okay, x squared, and then divided by 2 minus 1 divided by, now you got to have parentheses. Okay, you can't just type 2x squared, otherwise it's going to take the x squared and multiply it in the numerator. Now where are we in our parentheses? We need to close off our y prime, square it, and then we close it.
And then you question mark, or comma.
Question.
Yeah.
Comma.
Then you comma. Okay, so sometimes this can get a little bit crazy. I'll try to show the ones that go together here.
I use more precision. I do that too. So I close all my fractions. So I like 2 times.
Oh, you even put parentheses around your fractions.
I put yapping around the
Oh
front.
yeah, so do I.
Makes it easy.
So there's going to be even
I
more.
have probably 4 more parentheses.
Okay, so let's try this. Math 9.
Simpler way to do it would be to graph it in the things.
So I would say the hardest part is putting this in your calculator. All right, and then comma x, comma 1/2, comma 2. It looks like we'll get a fraction for this one. 33/16.
Or is it just 33 over 16?
Label what?
Like, now it's the length. Is it like inches or?
Oh, this calculus doesn't really concern itself too much, unless it's a word problem.
Okay.
Then we do, which we have a good one coming up.
So right now we just write s equals.
All right, let's move on to letter B.
Does it have to be like a y equals, or does it matter?
Okay, here's the point. It doesn't matter. If you have a function of x, then you're going to use this. You could also have a function of y, and this would just change to y.
Okay.
And then you'd have dy. So it really doesn't matter. If, however, if you change to a function of y, you also have to change your limits of integration, remember, from the bottom to the top.
Let's do it that way.
You want to use function of y?
Both ways.
Okay. So if you use y's, then you're going from the bottom to the top. Does that make sense? So, either way works for me. I usually like seeing it y equals, and that's the way I did this. It'd be much easier to solve for x though, huh? All right, so let's get y by itself. So y minus 1 equals x to the 2/3. Y equals x to the 2/3 plus 1. Okay, and then once you have that, you find y prime. So we'll use our power rule, 2/3 x to the negative 1/3. Notice the constant over here drops out of our derivative. We don't care about that. You want to just leave it to the negative 1/3?
Yeah.
So let's go straight to our arc length. Oh, let's draw our arc length so we know what we're talking about here. So from 0 to 8.
So this is specifically length of the curve, not the length of a line it's connected to.
Correct. All right. So our s equals the integral from 0 to 8. And it's the square root of 1 plus y prime squared dx. So again, the trick is going to be putting this in our calculators. I don't know why I like to sketch it out sometimes. So help me out here. Parentheses?
But 2 over 3. But you can put 2 over 3 x and 5. Oh no. You put negative 1 over 3.
Okay, and then close it off.
No. Yeah.
Have to. And now we want x.
And then could you put negative 1 over 3?
Mm-hmm. Okay, now we have to go back and make sure that we square our entire derivative. Okay, so really we have to come back here, right, and add another parentheses. Right? Then we're going to square that, and then we close off the parentheses. So I'll show you where these go. There and there. And then here is the derivative. Okay, so go ahead and give this a try. Yeah, this one does take a while.
Not just typing it in though.
No,
It takes a while.
Calculator just set there for me.
Yeah, this one does take a while, huh?
I sat there for over a minute.
Not over a minute.
But you got an answer?
9.073.
Good.
Good, that's not bad.
Mine literally sat there for over a minute, alright?
Oh, the screen is like right on.
Wait, keep yours up there.
It's because the camera has on.
Oh my god. Put the square root in it.
You're still
Wait, yours
on.
is still thinking?
It's still thinking.
See? I wasn't exaggerating.
That's really funny.
Yeah, this would not be fun to integrate by hand, would it?
Oh, what's the worst that could happen?
I don't even know. I don't think we have the
Oh, there
techniques to
goes.
do it yet.
That's really funny.
I think if we had solved for x, we could have done it, but there we go. Very cool.
Would that be implicit integration?
Yeah, we're gonna talk about a few of those things later. All right, our next one. Oh, natural log. We gotta remember.
Like 1 over.
Hmm. Isn't it?
Or is it the other way?
Isn't just u prime over u?
I have no idea.
It is.
Ew, I don't want to do
Long
these
ago. Not really for me.
Okay. Yeah, u prime over u. So here, so u is going to be cosine x. U prime is negative sine x. So u prime over u will be negative sine x over cosine x. And we can change this into one function, right? Tangent. So negative tangent x. All right, so this one will be a little easier to enter into your calculator.
Just a little.
Just a little bit. So we have 0 to pi over 4. Let's go ahead and draw where that is. So that's pi over 2. So pi over 4 is right here.
Oh, I wasn't. Thanks for reminding me. Smallwood.
Degree.
The Smallwood. So Smallwood, are you bringing the extra weight?
Mine.
Okay. I think this one we can handle without writing out the.
I don't know.
Think so? We'll give it.
drop mine. And you dropped it again? Where'd it go? Oh, there it is.
But you need another squared around.
That should be right, right?
That is right. And then
Okay, so what am I missing here? Oh, let's check my mode. Haha. There we go. 0.88.
wait, how did your answers? How did you change mode?
You go to
It's the last
mode.
problem.
The last problem didn't involve pi, so it didn't matter.
Or functions. I mean, trig functions.
Yeah, there are no trig functions. Okay. And coming to our final example. We'll do it. So an electric cable is hung between two towers that are 200 feet apart. The cable takes the shape of a catenary whose equation is, oh, you can see it right there. This looks like something that we did last chapter, right? Finding the derivatives of exponential functions. And we actually had problems that looked very much like this. And here is kind of an application of why that is. Because it gives us a catenary curve, which is the shape of, you know, any cable that hangs between two objects. It's actually a catenary type of thing. So you can see this would be a pretty useful application if you are figuring out how much cable you need to run your electrical wires. Because notice it's going to be a little bit more than the distance between the cables. Okay, so there's your cable. Now let's go ahead and graph this. We want to see what it looks like. So we got 75, because we need to figure out our limits of integration. E to the x over 150 plus negative x over 150.
Wouldn't the limits of integration just be 0 to 200?
I'm just going to do zoom fit.
800 feet apart, so
Well, we don't know where the curve falls in those 200 feet.
Oh.
So you can see the curve right there actually goes. Okay, that's not 0. Let's look at our window here. So we got negative 10 to 10. Well, that's not good because we need 200 feet apart. But notice the graph goes down right in the center of that. So this towers are centered around the y-axis. So we need to go like negative 100 to 100. Now, we want to be able to see the ground, so we'll just start at 0, and we'll go up to like 200.
Found it.
There it is.
That's what it actually looks like.
That's what it actually looks like. Yeah. So you can see, you know, it's 150, the cable's 150 feet off the ground at its lowest point right there. Okay.
with 200-foot tall towers.
I
I don't think the height of the tower changes it.
I don't know if we know the height of the
No,
tower here.
The towers are.
They're 200 feet apart, which means negative to positive 100. But
How come we didn't draw the towers?
Come on, calculator, draw the towers. All right. So that's kind of our drawing here. And we want to find how much cable this is. All right, so let's find y prime. Notice the 75 doesn't change anything. And the derivative of exponential function is just e to the u du. E to the u du. So it's going to be e to the x over 150 over 150. Now the next one e to the negative x over 150. And then du is negative 1 over 150. Uh-oh. There we go. Sorry. Is everybody okay there? So you can type this in. We could simplify this a little bit, because notice we could factor out divided by 150. And so it's really 75 over 150, which is 1/2. Put the whole thing over 2. So e to the x over 150 minus e to the negative x over 150 over 2. So s will be integral from negative 100 to 100 square root of 1 plus the derivative squared. Just put f prime here, or y prime. This one's the fun one to put in the calculator. So I'm going to write this one out.
That should just be the final answer.
Okay, so we got the 1. So we're going to open up 1 for the derivative and 1 for the numerator. Okay, so we're going to close the numerator, divide by 2, close the derivative, square it, and then close the radical. Whew.
That fish is a little long. That's what I got.
All right, and let's see what we get here.
Yeah.
There we go. All right, so that is finding arc length.